Buongiorno a tutti. It is my great pleasure to welcome Francesca Arici. She used to be Italian, now she's Dutch, so I should say maybe Goedemorgen.
Goedemorgen.
And we are very happy to have her. She's our dear friend, colleague, and collaborator. And today, she will be merciless at splitting our extensions of KK-equivalences for quantum projective spaces, which of course are given by graph algebras. Francesca, the floor is yours. Take it away.
Thank you very much for the introduction. And indeed, the topic will be something about graph algebras as the topic of all these conferences. I'm very happy to report about this work here in this conference because I think it fits very well the topics. And this is joint work with my collaborator, Sophie Emma Zegers, who used to be called Mikkelsen, in case you saw other papers she authored. I put the archive identifier now. This is published in the Münster Journal of Mathematics. So this is our COVID project because it started on March 3rd, 2020. So Sophie came for her environmental exchange to Leiden, and then after 11 days she had to flee to Denmark. This was motivated by some conversation we had because both Sophie and me are interested, in graph algebras, but also in non-commutative topology, like understanding non-commutative spaces from a perspective of classical topology. So in this particular case, we wanted to understand the K-theory of some sister algebras that are called the Waxman. Well, you don't even need a sister structure, but for the graph algebras, you do. So these are Waxman-Soibelman quantum projective spaces, and we wanted to study their KK theory. So KK theory is this bivariant theory due to Kasparov that generalizes simultaneously K homology and K theory for sister algebras. And in particular, what we wanted to do was constructing an explicit equivalence between the continuous function on these quantum projective spaces and continuous functions on the classical projective space. And in order to show you how we achieve this, I will go through these 3 stages that I've listed here. So first, I will introduce the algebras that we're going to study. So the Waxman-Soibelman quantum projective spaces. And in particular, I will describe how they can be realized as graph algebras, because that's also crucial in our treatment. Then I will give an overview of KK theory and KK equivalences and explain why we're interested in this kind of equivalences between sister algebras. And in particular, I will focus, as the title says, on the case of split extensions in KK theory. And finally, we will show indeed that there is a splitting for the extensions that define the quantum projective spaces and use that to prove our KK equivalence result. So let me first start by telling you something more about these algebras. So VS again stands for Waxman-Soibelman. These are quantum projective spaces. We denote them as CP and Q, and they are defined for any n greater or equal to 1. They are basically Q deformations of classical projective spaces. And like their classical counterparts, they have a quantum homogeneous space structure, meaning that we can realize them as quotients of odd-dimensional spheres by an action of the circle group. This is exactly the same as what happens in the classical setting, where as well you have that the quantum projective spaces are fixed points for an action of the circle on an odd-dimensional sphere. What is interesting is that this odd-dimensional spheres, the Waxman-Soibelman odd-dimensional spheres, have likewise a quantum homogeneous space structure, and they are quotients of SUQ n+1 by SUQn. This again is the same as the classical case where that we would have that the odd-dimensional spheres are homogeneous spaces for the special unitary groups. But they also have, so this is one way of realizing them as quantum homogeneous spaces, is first construct the odd-dimensional spheres and then act with the U1 action. But there is also another more direct way to obtain the quantum homogeneous, the quantum projective spaces as quantum homogeneous spaces, and that requires an action of the unitary quantum group on n generators onto SUQ n+1, and then the quotient is really the complex projective space. And again, this is also a structure that is there classically. So this is another way of realizing complex projective spaces as homogeneous spaces. Now, this will come back later when we discuss KK equivalences in a more abstract fashion. But for now, let me just tell you what these algebras are. So we fix a parameter Q between 0 and 1, so real parameter. And we first define indeed the continuous function on the odd dimensional spheres. This is the universal C-star algebra generated by n+1 elements, Z0, Zn, subject to some commutation relations that I've listed here. So the first two relations here really come from the quantum nature of those spaces. So if you were working with commutative spheres, so classical spheres, then here the parameter Q would be equal to 1, and you would just have that the variables in your polynomial ring are just commuting. So this is the deformation. Now this part here is what we call the sphere relations, and it encodes indeed the fact that these spaces are spheres, so they are so we can parameterize them by looking at complex n-tuples of numbers and ask that these points that have a coordinate given by these n+1 numbers have distance 1 from the origin. And this is the Euclidean distance. But of course, we are in a non-commutative algebra. So when we commute the adjoints the other way around, we have to be careful. And this is how the commutation relation works in that case. Again, needless to say, whenever you plug in the parameter Q equal to 1, then this part vanishes and you get the variables commute with their adjoints as if they should in this polynomial ring. All right. So, and then we want to construct, as I said, the quantum projective spaces as quantum homogeneous spaces for a U1 action on this odd dimensional sphere. And this we do by considering the following action. So we map the element Zi to omega times Zi when omega is any of the elements in the circle. Now, if you define such an action on the C-star algebra, you get that the fixed point algebra is generated by elements that are of this form. So they are Pij is equal to Zi star Zj. And the commutation relations inside this quantum projective space are deduced by the ones from the sphere that I wrote above. Particular, you may be wondering why I'm using the letter P, and that's not a coincidence. You get that the Pij's are entries of an n+1 times n+1 matrix that is a projection. So the commutation relation in the quantum projective space in this picture are given exactly by requiring that the Pij's are entries of a projection. So Pij, Pjk summed over J is equal to Pik. So this is just saying that P square is equal to P because it's a matrix. And then, of course, projections are self-adjoint, so we also have that. Now, interestingly, if you put n equal to 1, what you get is should be a complex projective line, or if you want, a two-dimensional sphere, and that's exactly the standard Podeles sphere. Okay, so this is one of the pictures of the quantum projective spaces, but as I said, these algebras are actually graph algebras, and this was realized in 2002 by Ong and Szymanski. So they have a paper on quantum spheres and projective spaces, and they show that the quantum spheres, actually all of them, but in particular we're interested in the odd dimensional ones here. So these quantum spheres and the quantum projective spaces are actually graph algebras. So let me first recall what I mean by a graph algebra. I think most people that are in this conference are very much familiar with this notion. But I will go over the definitions because in the case of complex projective spaces, we have infinite emitters, so it's better to fix some convention there. So a directed graph is a quadruple, where we have two sets, E0 and E1, and two maps R and S. E0, E1 are countable sets of vertices and edges, so we don't put restrictions about the finiteness of this set. And then we have two maps, RS, these are the range and source maps. So they basically tell us if we have an edge between vertex V and vertex W, we call it E, Then the range of E is the range, so the point where the vertex stops, and the source of E is V, which is the point where the edge starts. Of course, if you're in the other hemisphere, you may use a different convention, but for this talk, I will use this convention here, which is more natural for one graph, less natural for K graphs. But since we're talking about one graphs here, it seems more convenient. Okay, so we call a vertex in our vertex set regular if the pre-image of the source, which is the elements in the edge set that have a source in the point V, is either finite and non-empty. If we contradict either of the two, we have two special cases. If the pre-image of a certain vertex is empty, then we call this vertex a sink, meaning that nothing exits this vertex, and that motivates the name. And instead, if there are infinitely many edges that start at that vertex V, then we say the V is an infinite emitter because it emits infinitely many edges. And now we can define a C-star algebra associated to any of those directed graphs as follows. So given a directed graph E, we define C-star E to be the universal C-star algebra generated by some projections, PV, associated to each of the elements in the vertex set, and partial isometries as C, each for every edge in our graph, and such that we have these conditions. So every projection is orthogonal to any other projection. Then when we take SE star as F, this is 0 if the two edges are different, and this means that we cannot go back on that vertex, on that edge, because, well, if E and F were the same, then it would make sense to go back after moving forward on one edge. But since the two edges are different, there's no relation to what happens when we look at these maps. As said, if we do SE star SC, then that's the same as doing projecting onto the range, because first we move forward and we move back. The other way around. And then when we have SE star, this has to be bound by the projection onto the source. And this is these are basically the Kunz-Krieger relations, if you're familiar with Kunz-Krieger algebras, that are just a generalization. Finally, when we want to write out the projection onto a particular vertex, we can split it into a sum of SE star. So these are also projections, and now E ranges over all the edges that start at point V. Now, this relation only makes sense if V is regular, because either in the other two cases, we either have nothing that starts at the point V, or we have too much, we have an infinite sum, so we cannot make sense of a formula like this. But altogether, these 3, 4, and 5 are exactly a generalization of the Kunz-Krieger relations. Now, once we have such a graph algebra, we also have a canonical U1 action on this algebra, which is called the gauge action. And this is defined by keeping the projections fixed and by just multiplying one of these partial isometries as E with W, where W is an element of the circle. So the idea is that this U1 action comes from saying that the projections have a degree 0, and the partial isometries have degree 1, and their adjoints degree -1. So this turns our C-star algebra into a Z-graded algebra, and then you can use the Z action to define a U1 action. The Z grading to define a U1 action in a canonical way, because you just multiply by powers having the degree of the element you're acting on. Now, Ong and Szymanski, as I said, in 2002, proved that the C-star algebras of the Waxman-Seuberman odd-dimensional spheres are graph algebras for a particular graph that they call L2n+1. And I drew it here for you. L2n+1 is a graph that has n+1 vertices and one edge from Vi to Vj whenever I is smaller or equal to j. So this means, in particular, I wrote here L7, so n is equal to 3. n+1, okay, correct. N is equal to 3, so we have 4 vertices, and then we have edges moving only forward. So from 1 to 2, from 2 to 3, from 1 to 3. But of course, as said, this we have this condition here, so we don't have them in the other direction. And then we have loops at each vertex, because this condition is also satisfied for I equal to j. Now, if you were to write down the incidence matrix of such a graph, this is an n+1 times n+1 matrix. It is triangular with all ones in the upper triangle. Here. All right. And what is crucial about the result, which is a very profound implication, is that if you prove that this sister algebra is a graph algebra, then immediately you get that all the sister algebras are isomorphic for Q between 0 and 1. Because in the relations of graph algebras, of the graph algebra that I wrote here, the parameter Q does not appear. So if these sister algebra are graph algebras, then they are the same algebra for every Q. Now, the proof is highly non-trivial. It requires some, I would say, analytic continuation argument to show, to construct a very non-algebraic isomorphism between the generators in one picture and in the other. But the consequence is that one gets a very neat description of the sister algebra that is extremely combinatorial and also very easy to draw. As we say, graph algebras are sister algebras, one can see, right? So this is the one example. Now, graph algebras, as I said, come with a U1 action. And interestingly, if you identify C star of L to n+1 with the continuous function on the odd dimensional quantum sphere, then the gauge action gets mapped exactly to the U1 action that you have naturally on spheres up to a Q. I mean, there's this Q parameter going around, but you just act on the generators as I showed. So it's the same action as the classical one. And then if you look at the fixed point algebra for this action, then you can define this to be your quantum homogeneous space that you want to study. And this is continuous functions. Oh, sorry, my pencil is, okay. Continuous function on the n-dimensional complex projective space are the fixed point algebra for the gauge action. And they turn out to be also graph sister algebras. There is a whole theory about how to construct quotients of graph algebras by defining an action on the graph. And the resulting graph that you get is the following one. It still has n+1 vertices. Now we call them omega W1, W4, in this case of F7. And there are infinitely many edges between Vi and Vj when I is strictly less than j. So this is the graph, and you see that this is not row finite because it has infinite emitters. And it also has sinks because in general, Wn+1 is a sink. So here W4 is a sink because there are no higher vertices. So you cannot construct any error that goes out of it. So this is quite, let's say, quite a non-regular graph because, yeah. We have one sink and we have infinite emitters, so there are no regular vertices here. Okay, so however, we can still compute the K-theory of these quantum projective spaces. So if you're just new to the literature about graph algebras, you may know that in the row finite case, there's a way of constructing computing a K-theory groups, but this was also extended and generalized to the non-row finite case. The only small complication is that you have to be careful with what kind of vertices you're working with. So again, we like in the regular case, K-theory can be computed as kernels and kernel and co-kernel of a certain map. But in the case of a non-row finite graph, this map is a map defined on the free module over the regular edges to the free module over the edges. And in our case, we have 0 regular edges. So this is a map that goes from 0 to Zn+1. And the way this is defined is just by summing over the ranges of the edges associated to this regular vertex and then subtracted the vertex itself. And you see that the only way of making the sense of this map is to do it for a regular vertex. I mean, there's no way that this map can make sense for no regular one. But quite surprisingly, this is exactly the right thing. And needless to say, if you would have a graph that is row finite, so every vertex is regular. This is exactly the map that you consider in that case to compute the K-theory groups. So in our case, I said, there are no regular vertices, so we have a map that maps to Z to the n+1, and we get that the kernel is, kernel and co-kernel, So the kernel is 0 and the co-kernel is Z to the n+1 because the image is 0, so we're not quotienting by anything. And when you look at this identity here, well, these two isomorphisms of groups, you immediately see that these groups agree with the classical K-theory groups of the complex projective spaces. So there must be something there, and that's exactly the K-equivalence that we were after. Okay, but before that, I would like to say a little bit about the ideal structure of this graph algebras, and in particular of the projective spaces. So there is a notion of hereditary and saturated subset of the set of vertices in the graph. And this I will define afterwards. Well, it's there. You can already read the definition if you're interested. And once we get, the interesting thing is that starting from any such hereditary and saturated subset, we can get a K-J invariant ideal inside the graph algebra. And this in particular allows us to realize the quotient of the sister algebra of the graph by this ideal as a new graph algebra. So let me tell you what a hereditary and saturated set is. So it's a set of vertices that has the following property. First of all, if there is a vertex inside that set, and if we take another vertex, which is regular, then if there's a path from our V to this other vertex, then the other vertex had to be in H to begin with. And this is the hereditary condition. And the next one is the saturatedness condition. So we take a vertex that is regular. And then for any E in E1 that has the source in this vertex and range in the subset, then the thing we started from also has to be in that subset. This is the saturated condition. So it's a condition about what happens when we have a vertex in the graph that does not belong in principle to our set, but if it's connected to that set in some way, then it has to be in that set as well. Now you can see that if you look at the graph Fn, so the one for the projective spaces, then there's a sink is both hereditary and saturated. Sorry, here is 0. I said regular, but well, the second condition you don't check it because it's not there. So you only have to check the first condition. But you see that this is both hereditary and saturated. And if you remove from your graph this vertex Wn+1 and all the edges that go there, so this is a way of constructing a new graph, then you get a complex projective space of one dimension less. And interestingly, you get this extension that has that looks like this. So you get in the middle, you get the algebra of the complex projective space of dimension n. So this is C star of Fn. And then you have this ideal, which is generated by this sink. And then the quotient is an algebra, which is the algebra of the graph that you obtain by removing that sink and all the edges that go therein. So this is a very important extension because it allows you to recursively construct all the complex projective spaces from the ones of dimension less. And if you work it out for n equals 1, then you get that it simplifies very much. It's just a statement that the complex projective line is it's a unitization of the compact. So because in that case, you only, you are generating everything with only one vertex. And then when you remove all the edges, because you started with 2, you're just left with a C-star algebra over one vertex without any edges. So that's the complex numbers. And this sequence is known to split. So then it's natural to ask yourself, okay, what happens for the other sequences? Do they also split? And if so, can we say something about that? Splitting? Well, to find out why they should split, we hit the problem with KK theory. So maybe this was a bit of a big machine, but eventually it worked out. So KK theory, or Kasparov's bivariant K theory, is, I say, the bivariant theory for any pair of a separable sister algebra A and B, where B is also sigma unital. Kasparov defined the two Z2 graded groups that he called, defined the Z2 graded group that he called KK of AB. And this group, KK of AB, has a property that when you put the complex number as the first entries, you recover the K theory of the algebra, of the second algebra. And when you put and you put the complex number as a second entry, then you get the K homology of the algebra. And in particular, there is an associative and bilinear product. Also, this is an essential ingredient in Kasparov's work that goes from KK-iAB to KK-jBC. So you have to have the same entry in the middle to compose. And this lends into KKi plus j of AC. So here I and j are either 0 or 1 because this theory is, as said, is Z2 graded. And this product here, the Kasparov product, recovers, if you want, the index pairing, because when you put the complex numbers in the first entry, first entry here and the second entry there, then you get exactly the pairing between K theory and K homology. And here you would land into KKCC, that's not the integers. So it's really the index pairing. But it also has other interesting properties. Whenever you have a class in KK0 of AB, this induces a map in K theory from Ki of A to Ki of B. This is realized by taking the Kasparov product on the right with that class. Am I saying it correctly? Yes, on the right. And then KKBB is a ring, and K star of B and, well, K homology and K theory are modules over this ring. So we know we don't have a multiplicative structure in K theory, but at least we have this ring structure that is given to you by the Kasparov product. Okay, now comes the definition of KK equivalence. Two sister algebras A and B are said to be KK equivalent, or K equivalent. Sometimes that's a notion that is used if there are two classes, alpha in KK-AB and beta in KK-BA, such that when we take the internal Kasparov product of A with beta, alpha with beta, we get the identity in the KK group AA. And when we do it the other way around, when we take the internal Kasparov product over A of beta with alpha, then we get the identity in the KK group BB. So basically we have two classes that are each other's inverse, but whose products, of course, the products are, of course, in two different rings in principle. And two sister algebras that are KK equivalent cannot be distinguished by looking at their KK theory. So they have exactly the same KK groups, also for any other algebra as coefficients. There are many examples of KK equivalences everywhere in the K theory literature. So for instance, the complex number and C0 over 2 are KK equivalent, and this is nothing but the statement of Bott periodicity. So the fact that the KK theory is K theory is two periodic, and also KK. And whenever you have a complex vector bounded over a locally compact topological space, then the continuous function of initiating affinity on X are KK equivalent to C0V. And this is, again, a well-known result from K theory. This is Thom isomorphisms. And finally, whenever you have a Morita equivalence between two sister algebra, this is a particular case of KK equivalence, and the KK class implementing the equivalence is exactly the equivalence by module, so no operators. Now, there is a very important class of sister algebras that's called the UCT class. It plays also a very prominent role now in the classification program. And that's a class of sister algebras that satisfy the universal coefficient theorem of Rosenberg and Chauvet. And this is a very broad class of sister algebras. It contains all the commutative sister algebras, contains the complex numbers, I wrote K as AC, the compact operators, and it's stable under extension. So whenever you have two classes, sorry, two algebras that are in this class, then the third one is the extension is also in the UCT class. And in their paper, Rosenberg and Chauchet proved the following, that whenever you have two sister algebras A and B that are separable and that are inside the UCT class, then if they have the same K-theory groups, then they must necessarily be a KK equivalent. So this means that whenever you have an isomorphism at the level of K-theory for two algebras that are in the UCT class, plus separable, then necessarily this isomorphism at the level of a K-theory lifts to an isomorphism in KK, so to a KK equivalence. And this in particular applies to our case of study because of the extension that I showed you before. So since we have this extension that realizes the complex projective space of dimension n as an extension of the one of dimension n-1 by the compact operators, by induction, and by looking at the first case of this that contains K, CP1, and the complex numbers, then we get that all the complex projective spaces are in the UCT class, because the first one is, and then the second will be, because that's an extension of the first by the compacts, and so on.
By the way, if I might just jump in very quickly, this extension immediately allows you to calculate the K theory. So you don't.
Yeah, of course. Yeah.
One of these cases where you have no advantage by plate.
Yeah, that's also a way of constructing the computing the K theory, of course. That's very much the case, and you can get this extension without doing that all the discussion of the the ideals that I gave before. But this is a graph algebra conference, it works to see it also like that.
Which is in contradistinction to, and now Soren, please help me out. How do you pronounce Hira?
Sorry?
I'm asking Soren, can you help me pronounce Hira?
Hegel.
Hegel. So Tomek, you're almost right. Okay. So so this case is in contradistinction to Hegel, quantum complex projective space, because over there computation of K theory was very non-obvious.
Yeah, that's a completely different
story.
Yeah, I agree. Yeah. It's nice to mention it. I think I heard your first talk I ever heard, Piotr, was about that. It's nice.
Yeah.
Okay, so yeah, I said we get by induction that these algebras are to be in the UCT class. And of course, this result of KK equivalence using this UCT argument can also be obtained in yet another way and this was known in work by Sergei Neshveyev and Lars Tuze from 2011, where they show that if you have a continuous field of C-star algebras, if you have a quantum homogeneous space of the form GQ modulo KQ, so K is a compact subgroup inside the GQ, quantum subgroup, then you get continuous field of C-star algebra parameterized by Q, and this in particular tells you that the fibers at 0 and at 1 and all the fibers in between are all KK equivalents. So this is another way of seeing that. And as I said here, what plays a role would be the other homogeneous structure that I showed you, the one where you have where this is SUQN plus 1, and this is a UQN. No, the other way around, sorry. Need to wake up. Yeah, well, anyway, I showed you before. So you have UQ and SUQ. No, that was correct. SUQ n plus 1 modulo UQN. So this is more, yeah. So this is the quantum homogeneous space structure that you have there. Okay, so for now, what we know is that these algebras all have to be KK equivalent. So then the question started, okay, can we explicitly write down what this KK class is that implements this KK equivalence? And this is what we did in this in our joint work. And in order to do that, we looked at the theory of extensions and split extensions in KK theory. To be fair, KK theory was constructed out of extensions. I mean, the paper by Kasparov starts with that picture. So we consider an extension 0J-EB. So J is the ideal that sits inside this bigger algebra E, and B is the quotient. And we assume that this extension splits. So which means that we have a star homomorphism S from B to E, so from the quotient into the extension, such that when we apply the quotient map after it, then we get the identity on the quotient algebra. And then if you have an extension that has this extra structure, so this star homomorphism, then you can construct an element in KK J plus BE, then implements a KK equivalence between the direct sum of the ideal with the quotient and the algebra in the middle. And this element is very natural. It's a direct sum of the element J that describes the inclusion of the ideal into your extension, and the element S that describes how B sits inside E because of the existence of the splitting. Now, I write this direct sum, meaning that I'm taking the direct sum of the C-star algebra. So this class acts in the first leg on the first algebra and the second leg on the other one. So if you want to, I'm tensoring with the C2 here in the middle. Now, this class is a KK equivalence. So it has an explicit inverse that we denote by alpha. And the ingredients of this alpha are two classes. The first one is Q. It's just a class coming from the quotient. And that's a very natural thing, because when you compute it with S, you get the identity on B. And the other class is something that is called the splitting homomorphism. And it's a bit more involved to define, but I will recall in a second what it is. It's a class from E to J. So we need something. So we basically have everything except for one ingredient, right? We have a way to going from J to E and from B to E. So we sum them up to go from J plus B to E. And then for the inverse, well, we have the quotient map, which takes care of one of the legs of the direct sum, but we need to take care of the other one. And this is where thing is slightly more complicated. So I will describe this using Kuntz's picture of KK theory. So Kuntz in his work defined this KK group, KK-HAV, that cycles consist of pairs of star homomorphisms that go from the algebra A into the multiplier algebra of the stabilization of B. And these two star homomorphisms have the property that when we take their difference, the difference of their evaluation on an element of the algebra A, this thing has to become in this stabilization. So it has to be compact in some sense. Now, in our case, we go from the extension. What did I write here? J. Sorry, here there's something wrong. This should be a J. Okay, now maybe I should write it in white. Oh, no, sorry. That was correct. I mean, I'm explaining how to do it. So first of all, there is a map from E into the stabilization of E that just takes any element in your algebra E. This is defined for any C-star algebra, right? From the algebra to the stabilization, and you just answer with a rank 1 projection. And you just choose a rank 1 projection. Now, J sits as an ideal inside of E. So this has a consequence that there is a canonical map that goes the other way around. So it goes from the multiplier algebra of K tensor E into the multiplier algebra of K tensor J. And once you have this canonical map, then you can define the new map, compose with that, and then you get two star homomorphisms, Rj composed with EP and Rj composed with EP composed with S composed with Q. And this gives you a pair of star homomorphisms that is actually equivalent to taking just the identity in the first case and S composed with Q when you were to look in a graded picture. So this class here is the class pi that we need. And now we can take the direct sum of pi S with Q to get a class in KKE J plus B. Okay, so what does it mean? It means that whenever you have an extension of C-star algebras that have a splitting, then you can construct naturally and explicitly some classes. and those classes are implemented KK equivalence between what's in the middle and the direct sum of the other, of the ideal and of the quotient. Okay, so the way our proof of KK equivalence for these projective spaces with their classical counterparts work is to construct KK equivalence of this form, so via splitting. But of course, we need to find the splitting, and we need to know that we can expect to find the splitting. So how does this work? Well, we observe the following, that the splitting must exist because our sister algebras are in the UCT, and because of the kind of K-theory these sister algebras have. So this is very special. So there's a first lemma, that is what we proved, and later also, well, initially we had proven it only with one copy of the compact operators, but then we realized that this argument could be extended to any finite copy of the compact operators as an ideal. So this is how it worked.
Sorry, Francesca, can you remind me the nature of the splitting? What are the properties of the splitting map?
It just have to be, when you compose it with the quotient map, so first do the splitting, then the quotient map, it has to be the identity.
Yeah, but this map is what, linear, positive, or the
No, it's just a star homomorphism.
star homomorphism?
Yeah. So really split.
Okay, really split. Okay.
Yeah. Because I mean, everything here is a semi-split in principle, and then this gives you the 6-term exact sequence in K theory and K homology. You're really split. So it means that what you have in the middle is KK up to KK. It's a direct sum.
Okay. Thanks.
No problem. So it's very, it's quite strong. If you want, I mean, it's it's a very strong requirement. So okay, so what we proved is the following, that if you have a separable sister algebra in the UCT class such that the zeroth K theory group is free and abelian and K1 vanishes, then any extension of this form, so sorry, I wanted to use the pointer. Any extension of that algebra by a finite direct sum of compact operators is split, so really splits. Okay, and how does the proof work? But well, if you were to compute, so extensions of this form are classified by the group KK1A, KK1A, and then the ideal, and this you can write down as a direct sum of KK-AK. So you take m of them. Oh yeah, sorry, I accidentally deleted some things. And now you can use the UCT to write this as hom of K1A Z to the power m, direct sum of K0A 0 to the power m. And this is because, as said, K0 is free and abelian, so there is no x to take into account when you apply the UCT theorem. So let me just make a comment here. So this is the UCT. And then because you have this, you only have homs. And now here all of them are 0 because K1 of A is 0, and here we have 0 in the other leg. So what you get is that the group KK1A K plus M is 0. So any extension of A by M copies of the compact operators has to be a trivial extension. So, and trivial extensions are split. So any extension of this form is split. So this is a bit kidding it, but just saying, okay, can we double check that it has to be split? And it did work out that way. So now comes the interesting construction of the splitting. So now we're at the stage that we know we have a splitting. So how do we get one? And the way we tried first to construct it in the other picture. So in the more classical picture where you have spheres and fixed point algebras, but this didn't really resonate. I mean, for some reason, we couldn't single out what this map had to be, and probably rightly so, because this map is really, really explicit and very simple when you work with the graph algebra picture. And as the isomorphism between the two pictures is not so simple, that makes sense that we couldn't guess the splitting in that setting. So this is how we do it. So remember that we have this picture, this graph picture where we can get the graph when we call them Fn, the graphs for the complex projective spaces. And we obtain Fn minus 1 by removing the last vertex and all the arrows that went there. So this is here is Fn minus 1. So we have n vertices and we have infinitely many edges between them. And now we want to define a splitting. So we want to go the other way around. We want to go from the sister algebra of Fn minus 1 into the sister algebra of Fn. And how do we do it? Well, first of all, we observe that a sister of n minus 1 is generated by PVI and partial isometries. The same we have here. Now we call them, for a convention, we call them W and F. So the VIs are the one degree less, and the W are the ones 1 degree up. And now we just do like this. So whenever we are between 1 and n minus 1, we just map them correspondingly. So we map a PV, the projection onto the vertex VI, into the projection onto vertex WI. But then to take care of we have an extra vertex in the other algebra. So then the nth one, we map to a sum of the two projections. So if you want, for those vertices here, there's no problem. They just go to the corresponding vertices in the bigger graph. And then this one has to be mapped to the direct sum of the projections onto the other two vertices. And likewise, for the edge partial isometries, so the partial isometries labeled by the edges, as long as we have J different from N, we just map them really 1 to 1. So like, look at what happens vertically. And then if we have that one of the labels is N, so meaning that these partial isometries are going into the last vertex of the smaller graph, then we map them to the sum of two partial isometries that go from the same vertex, but to the other two vertices, to the last two vertices in the bigger graph. And turns out that this is the right map to consider, that when you apply Q after it, you get exactly the identity on the smaller graph. So the map Sn that we define like this is a splitting for the short exact sequence that gives the complex projective spaces as an extension of the lower dimensional complex projective spaces by the compact operators. And in particular, once we have this, then we get that the map J plus Sn that I described before is the map implementing the KK equivalence between the direct sum of K with the complex projective space of dimension n minus 1 and the complex projective space of dimension n. Sorry, so I'm missing bracket. So this is the K equivalence. Of course, the other side of the KK equivalence comes from the splitting homomorphism as I described, and now, okay, there are copies of compact operators, but up to Morita equivalence, this just says that you have a KK equivalence between the complex projective space of dimension n and this algebra of continuous function on n plus 1 points, which is in turn by classical arguments KK equivalent to the classical projective spaces. And that is the end of my talk. So the upshot is that this splitting had to exist, and we knew it had to exist because of KK reasons. And then the graph algebra picture was really the right picture to consider here to make this construction, because that was the only way of seeing this splitting very explicitly. And as you say, it's a very natural way. You just have these two graphs and map. In the first legs, you just map vertex and edges to the corresponding ones. And then when you have this extra part, you just split out somehow. So that was very natural in this picture, and once you see it, it's not surprising that in the more classical picture we couldn't guess what this would be. So, and with this I conclude my talk, and thank you very much for your attention.
Thank you so much. Now we have plenty of time for questions. Please allow me to begin because I cannot wait. Maybe it's very, very naive, but what happens for Q equal to 1? I mean, wouldn't it mean that we have a retraction? the inclusion. I mean, you surely can include CPN -1 in CPN, right?
Yeah.
Yes, they have stopped. No.
No, but this you don't have classically, right? This works in the graph picture.
Come on, grab a mic.
But Francesco already says that
Yeah.
this is for Q.
From 0
making
to
this,
1.
sister graph algebra. You cannot go with terms with Q to 1.
Okay, so this is purely quantum effect. That is what.
Yeah, it's purely quantum. Yeah.
Okay, okay, and
it makes sense, right? Because if it was in the other picture, then you could put maybe Q equal to 1 and make it work. But of course, it didn't work because
yeah, exactly. No, that makes sense. But what happens with this UCT argument? I mean, you have a very similar short exact sequence, all sister algebras UCT. So what fails on the conceptual level?
Let me think. Wait, I thought about that actually. Oh yeah, but because then it's X'd by the compacts.
Yeah, but instead of compacts, you have.
But then when you're commutative, then you
from open ball.
So KK1 of AB class. Sorry, KK1 of C. The other way around. KK1 of AC, where A is commutative, classifies extensions of A by the compacts. So not extensions by a point or like you would have, you would expect. So then that's why it fails. I mean, it says something about extension of this continuous sister algebra by the compacts, but not.
Can you write it down?
Yes, of course. So if you have, okay, let me see. So what we used in our case was that KK1. This was 0, and then we concluded that any extension of this form is trivial. But if you would, so if you prove KK1 of CA, if you prove that this is 0, so the K homology of A is 0, basically that's what we're using, then you're already saying that any extension of this form splits. So there's no retract here because you have this algebra. You don't have points. You don't have a point anymore.
So you are saying that in this equation, right here, you can see my marking, right?
Yes.
If you would replace compact operators by C naught of R2n, then
no. What you have to replace by C naught of C naught is A.
Yeah, but then I'm confused. I mean, the only difference in the short exact sequence is that instead of compact operators, you have C naught of R2n. Sorry, writing with the mouse is tricky.
Yeah, don't worry.
Okay, so this is what replaces compact operators in the exact sequence. And somehow what I understand is that these KK properties of this commutative sister algebra are different from KK properties of compact operators, so that something goes wrong, right?
Yeah, because the problem is that then you have to, so then what do you say? This picture of K homology and extension, what it tells you is that extensions of this of the commutative algebra, the other one, the CPNs, by stabilization of the 0 of R2n, so then you have the compact operators showing up. So you can say something about extensions of this commutative sister algebra, but only by compact operators.
Okay, I've got you now. Okay, thank you. Sorry.
Of R2n. But here, because the compacts are the compacts.
Yeah. You have this lucky coincidence.
Stabilize. Yeah,
I've got you now. Yeah, thank you so much.
No, I was also confused when I saw it and said, okay,
Yeah.
well, it is applied
Okay.
to classical, and that's the reason. Yeah.
And if I understand you correctly, you had this splitting by some abstract KK argument, but to have it explicitly, this is very really
Yeah, this is the graph algebra. Yeah.
that's really beautiful. So you see, guys.
Yeah, and first you also have the extension, the fact that their KK equivalence is known from many, you can see it in many different ways by using UCT, by using quantum group deformations.
Mm-hmm. Oh, okay.
But to have it explicit,
Yeah. So you see, guys, in a way, graph algebras are better than classical space.
but they're more visible, let's say.
They have more properties. I find it's a very fascinating effect. Okay, so why now don't we continue with questions? Anybody has any questions? Soren, you have a hand raised.
Yes, there's something that keeps I'm confused about in this model because you know, there's a very old classification result for what we called amplified graph algebras. And this is from 13, something I did with Efren Ruiz and Adam Sørensen. So we proved that if you have a graph where all the vertices, all the multiplicities are either 0 or infinity, like in your graph, we prove that two graphs are the same if they have the same transitive closure. So that means that if you have like an indirect path, you can always put the direct path as well. And if you apply this to the list of just, you know, n vertices, and I need to move n vertices and infinite, and so on, just like the top row, then the transitive closure is exactly the graph that you have. But my point is that this is the same C-star algebra. So you maybe not in a natural way, they're isomorphic using classification, something like this. So my point is that you could draw a simpler graph, just a straight line.
Yeah.
And that would also give you the C-star algebra. But whenever people use it, going back to Hong and Szymanski, I guess, whenever they describe it as a graph algebra, they always choose this particular one that you also showed us. And I'm wondering why. I mean, does it really matter?
So maybe can I say something about this?
Okay.
Because this is something also that is covered later on, because I was not careful reading Hong Szymanski paper, that in the appendix there is a simpler graph for the sphere, which is also one line instead of one line and loops.
I see.
So then if you do the fixed point graph there, you get the one.
Yeah, no, the point is that in that case, the isomorphism is not U1 equivariant. Exactly, so they are isomorphic as algebras, but you don't have equivalence. So, but
so that there's a theory around this now. This is a more recent paper I did again with Efren, but Aidan Sims, another S, where we prove that if you have amplified graphs, they're only gauge invariantly isomorphic if they're the same. So these will be different. But what I think is strange is that there is no gauge action because we pass to the fixed point algebra.
Yeah, indeed.
So I'm wondering, what gauge action are we talking about?
No, I'm talking about spheres. So that also for spheres, for some reason, people kept using the complicated graph instead of the simple one. But in that case, there could be a reason that for the complicated one, this is a U1 equivalently isomorphic to the presentation of Waxman-Soberman. The other one is not. For projective spaces, maybe it's just habits because you don't have U1 action.
But you don't care.
Yeah, it's trivial in both cases. So,
well, I mean, I would like the more complicated picture to be essential somehow because I think it's more interesting. But then you need a gauge action, exactly. Okay, I'll look more carefully at.
Seems to be what Francesco says, right? At least for projective spaces, it shouldn't matter which one you take because Thanks for this comment.
Yeah, for this argument, it could work.
Yeah, and also I guess the R splitting will be the same. It's just we have less.
Yeah, for that, I mean, I think that you could just do the argument. It doesn't really matter for that.
No, exactly, but it would be
as it shouldn't. So
exactly. Thanks.
Thank you.
If I could continue this comment of Francesco. So People are used to describe mappings between complex projective spaces in terms of homogeneous coordinates in the classical case, which can be related to this U1 bundle, which is a sphere over this complex projective space. Okay, so what you are doing here means, because of what Francesco said, it cannot be lifted to an equivariant map between these U1 bundles, these spheres. But this is very interesting because classically, if you had one principal bundle, U1 bundle over complex projective space, you could pull back this principal bundle to create new bundle over this, let's say, bigger projective space. When this mapping you are pulling along is this retraction to lower dimensional complex projective space. And then you obtain, if this pullback was possible, you could obtain something which is very similar to a sphere, but it must be something very exotic. Okay, so I wonder, did you try to look at your retraction from this point of view? If you want to lift it to an equivariant map between the spheres, Waxman-Seiberman spheres, then maybe you cannot do this. So in a sense, you are constructing some obstruction to equivariant mappings between Waxman-Seiberman spheres. So maybe, yeah. So I'm wondering whether this construction would be used to construct some obstruction theory for equivariant maps between quantum spheres.
That's a very good question. I didn't think of that, but that sounds...
Because it's very interesting because, as Piotr said, this is purely quantum.
Yeah, exactly.
Classically, it is impossible. So it's worth to be stressed that the classical... So yesterday, I was talking about non-existence of this retraction. And even I was talking about some kind of additional topology on complex projective spaces coming from these U1 bundles over them, when you can use classical arguments showing you that such an equivariant lift is impossible. Okay, so everything looks like a very good starting point for some theory of obstruction theory for equivariant maps, using this quantum effect that at the base almost everything is possible, but this is very non-algebraic, very far from classical situation.
Definitely, yes.
Yeah. I mean, these generators is very algebraic.
Yeah, but these generators are not of geometric origin. They are different. They are these angular parts in polar decomposition of something which came from topology. But the point is that this radial part of this polar decomposition explodes at the classical limit. So yeah, it's a part of very fascinating story.
Yeah.
Thank you.
Thank you very much for this remark. Yeah. Should talk more about this.
Any other questions from the room or the Zoom? Okay, I don't see any volunteers. So in this case, Francesca, if you don't mind, could you please go back to this Waxman-Seiberman sphere picture?
Let's see.
So my question is deeply, I think you passed through. I want this identification of graphs. I want to see the graph.
Oh, sorry.
Oh,
yes.
yeah, here we are. That's as you mentioned, that this is a very non-trivial result of function monkey, but I know that Tomek and Francesco were digging into understanding the proof. So could you please, guys, comment on this? The question is not to you. It's
Okay.
it's about your talk, but it's not to you. I apologize for it, but it's
problem.
essentially related to your talk because you emphasize this point. And they recently did some digging with Jens Pod. And could you please tell us, comment on Francesca, whoever.
Yeah, there's a fishy argument, but the claim is true. There are some further works of other people filling this gap.
There is also, you can deduce this isomorphism from a more general result now of, for example, I think Matassa and Juncken, right? It should be a special case of, this is what I think Robert said at his talk, that in any case, this provides an alternative proof of this isomorphism.
It is indeed a tricky result.
Yeah.
All right, so I have one last comment. Could you please go back to this part in your slide when you had this algorithm for computing K groups? Oh, yeah. Oh, right here. You see? So yesterday, Tomek was emphasizing, Francesca as well, I guess, that if you look just at the abelian group structure, you cannot distinguish by K theory CPN and n-1 points. And if you look at this formula, again, the same is true because the commutative algebra of functions on endpoints is a graph sister algebra.
Yeah.
But all these and the graph is equal to the space. And of course, all these points are sinks. So there are no regular vertices. It's exactly the same calculation. I know it's a trivial comment, but I could.
No, it's not a trivial comment. It's the magic of graph algebras.
I'm connecting to previous talk.
Yeah, it's great that you do that.
Okay, guys, if there are no other questions, let us thank Francesca again. Grazie mille.
No problem. No, prego.
Okay, so I stop recording. Wait a second. Where is it? Where's the button?